Scree plots are also plotted. So you see on the y-axis, you have the eigenvalue of the factors. On the x-axis, you have the number of the factor. Uh, and we usually say that keep all those, retain the factors uh, uh, where you see the elbowing happen. So you need to check where the elbowing of the graph is happening. So in this case, for example, we can say 1, 2, 3, 4 factors, okay, or we can say only 1, 2, 3. Well, that is the problem with this kind of a plot. I would usually go with, if I were to just look at scree plot, maybe 4 factors can give us good idea. But if you look at eigenvalues, only the first 3 factors are good. So there are criticisms of this. There's no clear definition of what constitutes a major drop. Okay, and some data may produce a gradually decreasing slope. Okay, so yeah. The last thing that we will like to come to is factor rotation. Now, when we will do exploratory analysis, we will get an initial solution. Okay. Now, what we need to do is, in order to improve our understanding as to what is the major factor on which this particular item is loading, or a set of items are loading, we go in for rotation of the factors. Okay, and so the goal is to simplify and clarify the data structure. So what is the uh, major factor on which a particular item is going to load, and that is what we achieve using factor rotation. So let me just draw a diagram to help you understand how this works. So again, building on the previous example of I1, I2, I3, I4 and factors 1 and factor 2 that we have extracted, right? So this is our graph, factor 1, factor 2, and we have got, let us say, we have got I1 with its loading being 0.5, comma 0.5, okay. I2 was somewhere here, so we can say it is I2, it is 0.6, comma 0.6 again. I3 is another set of items, so we can have, this is I3, we can say it is minus 0.2, comma 0.6, and let us write it as minus 0.1, comma. Okay, actually, let me put it somewhere here. So it is minus 0.5, comma 0.5. Now, if you see, what has happened is, you have I1 which has loading on both F1 and F2, 0.5 and 0.5. I2 also has loading on both 0.5 and 5. Now, it is very difficult, if this is the solution, to actually say to which factor does I1 belong, whether it belongs to, whether it is loading to, whether we should retain it as an item for factor 1 or we should retain it as a factor 2. So what we do is, in this case, we start to rotate. We do a rotation, sorry, we do a rotation here of the axis, okay? And we call this as, let's say, F1 dash, and this becomes F2 dash. And now if you were to represent I1 again, okay, you will see because I1 is lying on, it will pass through this line, and let me draw it here, okay. We can say its component on factor 1 increases and its component on factor 2 becomes 0. Similarly, I2, if I were to write I2, maybe it increases a little bit. We can say it has become, and similarly I4, it has become 0, comma, 0.6, and let's say I3 has transformed a little and it has become, yeah, minus point, or it has become plus 0.1, 0.1, comma, 0.7. So now it is very clear after this rotation that I1 and I2 belong to factor 1 and I3 and I4 they belong to factor 2. So this is what rotation achieves, and this kind of a rotation is called as an orthogonal rotation. Orthogonal rotation, that means when the angle between the axis remains unchanged, it is kept as 90 degree. What does this mean? Orthogonality also means that the correlation between F1 and F1 and F2 axis is 0. That means the two extracted factors, they are uncorrelated with each other. Okay, they are. Now the problem with this, and this is popularly known as, this kind of rotation is popularly known as the varimax rotation. Varimax rotation. Now, the problem with this approach is, and the criticism of this approach is, that to assume that the extracted factors will be orthogonal to each other, okay, is a wrong assumption, is something that is not valid, something that should not be used in uh, in literature, in sort of analysis. It is because what we are trying to do, the idea of exploratory factor analysis was what? It was to test the dimensionality of our construct, right? Which was measured through the instrument that we have created. So in order to test the dimensionality of our construct, we performed exploratory analysis. Now, when we are saying varimax, we are essentially saying that the subdimensions, which are basically F1, F2 for our construct, these subdimensions are not correlated to each other. Now, this is a wrong assumption because these are dimensions of the same construct. It is very likely that these dimensions will be correlated. To force orthogonality, to say that these factors are not going to be correlated to each other is a very, very strong assumption and something that we should avoid. And so what we should be doing actually, and this is what is recommended in analysis, is that we should allow this axis to co-vary. Okay, we should allow these axes to co-vary with each other. Okay, look at their extraction, and this angle can be different from this angle is not 90 degrees. So the better way, and this is in literature, this is called as oblique rotation. In SPSS, there will be two options, Promax and Oblimin. Okay, for oblique rotation. And what does oblique means? That the extracted factors can be correlated to each other. So the recommended approach is that we should start with oblique rotation. The software, and we will just do it in a while now, the software will report the correlations between extracted factors. If correlations are small, say less than 0.3, you can go for varimax rotation. You can, it is not necessary, okay? Or stay with oblique solution. Otherwise, if the correlations are anyways large, you report the oblique rotation result. Okay, and that would be a better approach of doing your factor extraction. So what is it that we are recommending here, or we are talking about when we will do exploratory factor analysis? We will do principal axis factoring with oblique rotation. We will not do principal component analysis with varimax rotation.